Okay, so today we're going to do modeling with exponentials and logarithmic functions, which is 4.6. So the first thing we're going to do is look at exponential growth and doubling time. So you have this culture of bacteria. It's 10 bacteria and is observed to double every 1.5 hours. So we use the idea of a compound continuously formula, which states A equals P times E to the RT because it is compound continuously, observed and changes every 1.5 hours. So for part A, it says find an exponential model for the number of bacteria in the culture after T hours. They want me to form some type of a formula. So using what I do know, I know that the initial bacteria is 10, but I also know that it doubles every 1.5 hours. That tells me that my A value is going to be 20 equals E times the rate, which I don't know, so I'm going to find that, times 1.5. Remember, you cannot do anything until you find the rate of something when looking for a specific answer, whether it's initial or the actual final answer. So here I can go ahead and do some math. Divide by 10. Those cancel and you get 2 on the left side equals E the 1.5 R. Take the ln of both sides. Bring down that 1.5 R. Remember, ln of E becomes 1. So you have ln 2 equals 1.5 times R. Divide both sides by 1.5. That tells me that R, if you plug it in your calculator, gives you 0.46. That's not my final answer, but that will allow me to set up my exponential model. So I set up my exponential model by doing A equals P times E. My rate was 0.46 to the T power. So there's my exponential model. Part B says, estimate the number of bacteria after 35 hours. So I'm going to use the same setup. Have A equals 10, which is my p-value. E, my rate was 0.47. My time is now 35 years. So you can go ahead and plug that in your calculator. So after doing this in your calculator, you should get about 105,689,838 bacteria. All right, now let's look at part C. Part C says after how many hours will the bacteria reach 10,000? So we want to know at 10,000, when will that bacteria, or sorry, what is the time when it reaches 10,000? Times P, E to the rate, which is 0.47, times T, because that's what we're looking for. Divide both sides by 10. You're left with 1,000 equals P. I'm sorry, we should need to get rid of that P. Times E to the 0.47 T. Take the ln of both sides. Move that 0.47 T to the front. Remembering ln of E becomes 1. So you have ln of 1,000 equals 0.47 T. Divide both sides by 0.47. That means that T equals about 15 hours if you round. All right, let's look at example 2. It says a gray squirrel population was introduced in a certain county of Great Britain 30 years ago. biologists observed that the population doubles every 6 years, and now the population is 100,000. So again, it's still compound continuously. So we're going to use the formula A equals P times e to the RT. Understand that the population doubles every 6 years, and then the population after it has doubled is about 100,000. Understand that a gray squirrel population was introduced to a certain county in Great Britain 30 years ago. So the first question for part A says, what was the initial size of the squirrel population? So we can't solve and do anything unless we have the rate. So the first thing we need to do is find the rate using everything that talks about the biologist that is observed population doubles every 6 years. We need to use that information to help us find the rate. So for our rate, let's set up the equation. Well, we know that we don't necessarily know our initial size because in part A, it wants us to find the initial size. So we can say that the initial size is X, which means if we know the population doubles every 6 years, we know that the population will be 2 times as much as our initial. Times E, our rate we don't know, we're going to find that, times the amount of years, it doubles every 6 years. So let's solve this by dividing by X on both sides. We get 2 equals E times 6R. Take ln on both sides, bring down that 6R. Remember, ln of E becomes 1. So you have ln of 2 equals 6R. And divide both sides by 6, we get our rate to be 0.12, which means my equation reads A equals P times E to the 0.12 times T. So we can use this equation with the rate to help us find out exactly what is the principal. So I'm going to use this formula, but I'm also now going to use some other information that was given. So I'm going to use the information that the county of Great Britain was 30 years ago is when they identified this gray squirrel population. And I'm also going to use the fact that now the population is 100,000 30 years later. Or 30 years, yeah, 30 years from now, the population is 100,000. So I'm still working on part A to know what is the initial size of the squirrel population. So I'm going to use the formula that I discovered when I did the first part of the problem, identify R. Well, I know that the population for now, for the initial, to deal with part A is 100,000. So it tells me now population equals, I don't know what my initial size is, so I can label it as P, times E, my rate I found is 0.12, my time is 30 years. Now I need to go ahead and solve for this. I'm going to go ahead and divide both sides by E to the 0.12 times 30. So I can get P by itself. So you get P equals, when you plug this into your calculator, plug it in just as you see it, you should get 3,025 squirrels. So that is what your initial size of squirrel population was, is 3,125. Now let's talk about part B. Part B says estimate the squirrel population 10 years from now. So everything's still the same. We now can say that we want to know what is the population for 10 years. So we have to set up the population at 100,000 years. So we're looking for A. Our initial, we're starting off at 100,000 because it wants to know what is the population 10 years from now, times E. Our rate doesn't change, times the years is 10. So when you plug this into your calculator, you get about 317,480 squirrels. And yes, you could have this in a different manner. I believe that this probably will be the easiest way to set up part B. If you have another way that you set it up, just let me know and make sure that you get the same answer that I've gotten. Okay, example 3 says the fox population in a certain region has a relative growth rate of 8% per year. It is estimated that the population in 2005 was 18,000. Again, we're still using that formula A equals P times E to the RT. Part A says find a function that models the population T years after 2005. So A equals P times E. Well, we know our rate per year was 8%, which becomes 0.08 times our T. So that will answer part A of our question. Part B says use the function to estimate the fox population in the year 2003. So, well, we started off with 2005, and now we're talking about 2003. So the difference in the time of that for the years is 8. So A equals our initial principal is going to be 18,000. E times 0.08. Our times, our difference between 2013 and 2005 is 8. When you plug this into your calculator, you should get about 34,137. Part C says, after how many years will the fox population reach 25,000? So in this case, we know that we're looking for A is going to be 25,000 equals our initial, which is 18,000, times E, our rate is still 0.08, and we don't know the time. So we need to go ahead and divide by 18,000 on both sides. So we get 25 over 18 equals E to the 0.08t. Go ahead and take the ln of both sides. Bring down that 0.08t. ln E becomes 1. So we have ln of 25 over 18 equals 0.08t. Divide both sides by 0.08. If you do that, put this in your calculator first, and then divide the whole thing by 0.08, and you'll get roughly about 4 years if you round it to a whole number.